Okay, more fun with radicals on the way. All right, so here's the product rule and quotient rule that really we've already talked about in both sections. What it tells me is as long as they have the same index and I have things being multiplied only, right, then I can either separate them into their own radical, or I can put them under one radical and multiply, or divide, same thing, right? I can separate it in its own radical, or I can put them together into one radical, as long as the index is the same. So I want to remember this because, and it goes both ways, they're equal signs, so it goes both ways. I want to be able to do whatever helps me simplify those numbers the easiest. Sometimes I'm going to put it under one radical, so this number will simplify and then I can do the root. Sometimes I'm going to separate it and do the root individually. Okay. Now, I can't do the square root of 5 or the square root of 13. And so because they're multiplied, I know that, hey, well, I can put that under one root. Right? And then 5 times 13 is 65. So that's considered simpler than this. Same thing here. Since I can't do the square root of 7 and I can't do the square root of xy, well, at least I could simplify that since it's only being multiplied and put them under the same radical sign. Okay. Indexes are the same, indices. So 7 times 2 is 14. Cube root of 14. Okay. They both have an index of 6. So I can multiply 8 times 2 is 16. And r squared times r cubed is r to the 5th. Now, they're not giving you problems like that yet because we haven't had an explanation. But I always have to double check and see if I can write this with an exponent that's 6 or bigger. It could be simplified. This exponent, because 8 is 2 cubed, this is really 2 to the 4th. So as long as this index is bigger than my exponents, it can't simplify. But if I ever get an exponent bigger than the index, I'm going to have to simplify. So I got to think about that. Okay. So over here, because they're both a 5th root, I can put that under 1. 9 times 8 is 72. Y squared times y squared is y to the 4th. X times x, x squared. Because of where the 72 came from, I know that it's 3 squared times 2 cubed. And this is an exponent of 4 and an exponent of 2. So as long as all the exponents are smaller than 5, that's all I can do with that. Now be careful on this one. They are not the same index. I can't do anything with that. It's simplified as far as it can go. So be careful of that. All right. So here, we've already done several like this. This is just our quotient rule. It'd be, I see, because I know 100 and I know 81 are perfect squares, so it'd be real easy to just separate each one and then do the root first. Okay. On this one, the fraction won't simplify, but I can tell that I can't do the square root of 11, but I can do the square root of 25. So I'm still going to simplify it. I'm still going to use my product rule to help me simplify it. Okay, this one's going to be the cube root of 18. over the cube root of 125. And hey, the cube root of 125 is 5. So cube root of 18, I can't simplify that any farther. But the 5 I can. Okay. Now, here's what we were talking about. So the square root of 16 is 4. But don't forget, anytime you have an exponent bigger than your index, how many times does 2 go into 8? 4 times. I can simplify that. All right, this one has a negative out front. Now, the 2 is smaller than the 3, so that's not going to simplify. But the 12 is larger than the 3, so it needs to simplify. How many times does 3 go into 12? 4. Okay, here's our conditions. How we know we're finished simplifying. The radicand, the number underneath the radical sign, cannot have a power that's greater than or equal to the index. We were just talking about that. You cannot have a fraction under a radical sign. You cannot leave a denominator under a radical sign. Okay, so exponents in the radicand and the index have to be prime. They can't have any factors in common other than 1, meaning they're prime. Okay, so we were basically already discussing that, except remember, no fractions can be left under a radical, which means no denominator can have a radical. Oh, come on. Okay, so here we're getting down to it finally. 32 is not a perfect square. So right now I might be thinking, oh, well, then I can't simplify this. But I don't want to do that. I want to write this with exponents on it. So if I write this with exponents on it, and maybe the easiest way is just to do our prime factorization. Remember this? Keep up with all your prime numbers. So that means I can really write that as the square root of 2 to the 5th. Okay, now I've got a 2 here. So my question is, how many times does 2 go into 5? It goes in 2 times. I can take 2 out, but there's 1 left over. Right? So the ones we've done before, it went evenly. But I can have a remainder. It's just that part remains under the radical. All right, let's try this one. 3 times 100. Okay. And so that's 10 times 10, which is 5 times 2 times 5 times 2. So I can change that to the square root of 2 squared times 5 squared times 3. That's the same thing as 300, right? Now this time I'm going to separate it, but eventually I want us to just get used to doing it without too many steps, so think about this. We've got that product rule that says I can simplify them under their own radicals. That means this square and that square root will undo. Or how many times does 2 go into 2? 1 time, so I can bring 1 5 out. Okay, but that's an exponent of 1, so these don't have any factors in common. It would just stay under there. So from up here, think about this. 2 goes into 2 1 time. I could bring out 1 2. 2 goes into 2 1 time. I could bring out 1 5. 2 does not go into 1. So this remains under the radical. Hey, that one doesn't have any exponents. It doesn't simplify. There are no exponents 2 or larger. These simplified because when I wrote them in their exponential form, when in their factored form, I had exponents 2 or larger. If none of them have exponents larger or the same as the index, it doesn't simplify. Okay, let's try it again. It doesn't even matter what my index is, right? They work exactly the same way. So let's write 54. What is that? Maybe 9 times, whoops. Why am I circling that? 9 times 6. And 9 is 3 times 3, and 3 times 2. Those are all primes. So I can rewrite this as 1, 2, 3, 3 cubed times 2. It's still 54, right? But now 3 goes into 3 1 time. So I can bring 1 3 outside. 3 does not go into 1. So the 2 remains inside. Don't forget your index, because that's different than a square root. It's a cube root. $243. I hope we recognize that as 3 to the 5th. We've seen it several times. If not, we can still do our 3 times 81. 9 times 9, which is 3 times 3. And 3 times 3. So I can write 243 as 3 to the 1, 2, 3, 4, 5. 4 goes into 5 1 time with 1 left over. So I can bring 1 out, but there's 1 left over. It doesn't go evenly like this did. All right, I'm going to do my numbers and variables separately. This one's not too bad because it's the square root of 25. And variables are easy because they're already in exponential form. So how many times does 2 go into 7? 3 times. You can bring 3 p's out, but that's only 6, so there's 1 p left over inside the radical. Okay, I can't do the square root of 72 like I could 25, so I need to see all my exponents for it then. Okay, so I'm going to change that to square root of 2 to the 3rd times 3 squared, 8 times 9, and then my variables, they work out nicely. Make sure you draw your bar long enough. Because if I didn't cover that x, it means it's not actually inside the radical. So be careful of our notation. Now this is a 2. So how many times does 2 go into 3? 1 time, so I can bring 1, 2 out. But there's 1 left over. How many times does 2 go into 2? 1 time, so I can bring 1, 3 out. And there's nothing left over. It goes evenly. How many times does 2 go into 3? 1 time, but there's 1 left over. How many times does 2 go into 1? It doesn't, so I can't bring any out. Now here's some math I can do. So this is 6y times the square root of 2. You can put yx, it doesn't matter. 2 times 3, 3 times 2. We generally put the variables in alphabetical order, but it doesn't matter. Okay, let's do some more. Okay, a cube root and a negative. So really I already know that the negative is going to be out here, right? Because the cube root of -1 is negative. Cube root of 27, that's 3, right? 3 times 3 is 9 times 3 is 27, so I can bring that out. 3 goes into 7 2 times, so I can bring 2 y's out. But it doesn't go evenly, so there's 1 y left in there. Because 3 times 2 is just 6, and I needed 7. 3 goes into 5 1 time, but there's 2 left over. 3 goes into 6 2 times with none left over. I'm going to rewrite this just so it's a little more clear. 3y squared x z squared, and then the cube root of x squared y. Just like we always say, just keep simplifying. Make sure, double check that you don't have any exponents in here bigger than your index. If you do, you're not finished simplifying. Okay. 32, I need to see its exponent, so maybe that's 2 times 16, 2 times 8, 2 times 4, and 2 times 2. So I can rewrite that. The negative is outside as the 4th root of 2 to the 1, 2, 3, 4, 5. Then I've got an a to the 5th and a b to the 7th. 4 goes into 5 1 time, so I can bring 1, 2 out. But there's 1 left over. 4 goes into 5 1 time with 1 left over. 4 goes into 7 1 time with 3 left over. Notice all exponents inside the radical are now smaller than the index. Okay, last one. Let's see what we're doing. I've already got the answer up there. Well, part of the answer. I was supposed to take this off. So let's ignore that. Okay. So one thing we can do if we're needing to simplify still, but 12 doesn't go into 3, right? Then I can change this to the exponential form so that I can reduce the fraction, because remember we said they also can't have any factors in common. That's why I know I'm not done here. My index and my exponent can't have any factors in common, because look, I can change it to its exponential form, okay, and then reduce that fraction. Now, I can put it back. I can leave, this doesn't really tell me how to leave it. I can either leave it in exponential form, or I can put it back in radical form. Okay, so this one, because they've got factors in common, what I'm thinking of is, well, let's change it to its exponential form so I can reduce that fraction, and then I can put it back if I need to. Okay? All right, have fun.